Today, we'll be talking about spherical coordinates. So, spherical coordinates. If you want to find some hypervolume, shout out to bro in a previous comment section. He told me the terminology in the comment section. But if you want to find a hypervolume or some shape in four-dimensional space, you need to use a triple integral. And sometimes when you're integrating over a volume, it's going to be shaped like a sphere. So, this spherical coordinates that you're going to learn today is going to be a very, very useful tool whenever you're integrating over a volume of a sphere. So, first things first, let's describe the units or the variables that we're going to be using. So, wrong thing. So, variables will be, first one, it's called rho. It looks like a P. It's not actually a P, but it's called rho. And honestly, you can just write it down a P, same exact thing. And the next variable will be phi and theta. So these are the three variables that you're going to be using for spherical coordinates, and I'm going to show you what these actually look like. I'll also show you the transformation factors, like what x is equal to, what y is equal to, what z is equal to, and what the v will be equal to in this case. So let's show you visually first. And notice I had to draw this beforehand in the beginning of the video because I'm not a good artist and this was kind of difficult to draw. But let's start off with a green arrow. Do not worry about this green arrow for now. Just know that it lies flat on the xy plane. And then let's draw a blue arrow angled up like this. And as you can see, this blue arrow is right above the green arrow. For now, ignore the green arrow. But this blue arrow is what we call rho. So just like in spherical coordinates, you're going to have some radius, r. In spherical coordinates, you had a value r. But in polar coordinates, you had some value r. But in spherical coordinates, you have something called rho, and this is rho right here. It's simply your radius of your sphere. And maybe if you had a tiny little sphere inside here, your bounds would be from 1 to like 3 for your rho integral. But just know that your rho integral is just the radius of your sphere. Typically, it's going to be bounded from 0 to whatever radius you have of your sphere. So this is our rho value here, this blue arrow. And this blue arrow can be drawn anywhere. It can be drawn, let's say, like, that is not along the x-axis. Let's say, like here. It can be drawn like this, right? But your rho value is just simply, think about it as your radius of your sphere. As I repeated that like 5 times. How about your phi value? Well, your psi is different. Phi value is the angle between the z-axis. The angle between the z-axis and the rho vector. So this phi currently may be like, I don't know, 17 degrees. But if you want to draw the entire sphere, your your psi value, would keep increasing until this rho value reached 180 degrees. So this right here, this rho is at pi. So if you wanted to find the integral, and let's actually say the radius of this is 3 for now. So let's preset this. If you wanted to find dp, d phi, and d theta, currently this sphere is radius of 3. And if you wanted to find the radius, or if you wanted to define phi for an entire sphere, the bounds would just be from 0 to pi. And the reason why is because if this rho vector goes all the way down pi, or 180 degrees, starting from the z-axis, it reaches the bottom of the z-axis. And that already encompassed the entire sphere. How about your theta value? Well, your theta value is how much your rho vector or this representation of rho for now, is straying away from your positive x-axis. So if you want to encompass the entire sphere, your rho vector would be 0 to 2 pi, compared to phi, which is from 0 to pi. And I'm going to show you a representation of this, and your theta is simply this guy, this angle right here from the positive x-axis, and your blue vector. And currently this green vector right here is your blue vector projected down onto the xy axis. So imagine you just flatten it completely down. It's the projection of your rho vector onto the xy plane. And that vector you get there is the angle of phi. Now if you wanted to say, let's ignore this side of the sphere. Let's ignore this side of the sphere, right? The side of the sphere that is on the negative y-axis, so on this half right here. Then if you wanted to do maybe a half sphere, your theta value will be from 0 to pi. Therefore, your sphere only stretches from this right here, this x-axis, to the negative x-axis. And if you can picture that, it's simply just the sphere cut in half along the x-axis. Now that we have all the tools we need, we can actually start defining what x, y, and z are. So in polar coordinates, you had x is equal to r cosine theta, and y is equal to r sine theta. Now, you don't have to memorize this. This can be simply deducted, so to say. And the reason why is because in polar coordinates, I'll do a quick topic about that. But in polar coordinates, if you wanted to use, say, a vector, let's change the color actually. You wanted to say use a vector. Your x value would be the x value here, y value be with the value here, and the length of this red vector is r. So if you just find r of cosine of the angle theta here, defined in polar coordinates, you can actually get the x value along the x-axis. Same for the y value. If you multiplied sine by your magnitude of this vector, you would get the y value of your transformation. So for your spherical coordinates, you can do the same. So let's try to work out the logic of this. Let's say you wanted to find r, and your radius r is always flat in the xy plane, correct? Which is this green vector here. This green vector can also be lifted up a little bit so that the heads of the vector are touching. And I don't know if that's a good drawing of it. Let's try doing it like this. Hopefully, this is a very cluttered image, but hopefully you guys can understand what I'm saying with this. This green vector here is actually, these two are the same thing, but I just lifted this bottom green vector up along the z-axis so that the blue vector and the green vector are head to head. If you can tell what this is simply our r value. So we have rho. If we multiply rho by sine of phi, you can actually get this green vector here. And if you multiply the green vector by cosine of theta, so your phi angle is this and your theta angle is this. If you multiply rho by sine of phi, you will get this sort of green vector here. And if you multiply this green vector by cosine, you'll actually get its value here along this part. I need to change the color there. Along this part of the x-axis. How about the same for y? Well, you have rho times, again, sine of phi, and then you get the green vector down here again. If you multiply this green vector by sine of theta, you can actually get your y value. Now you can memorize this, but if you can work this out, or hopefully what I said was understandable, then you can actually work this out and you don't have to memorize this. But memorizing it, completely fine as well. I just recommend knowing how to do it. Okay, but your z value will be simply rho of cosine of phi. And the reason why is because if you find the cosine of this rho value, so rho is currently this blue vector here, find the cosine of this along phi, you'll actually get this little length along your z-axis, the purple color, if that's visible. So these are transformations in this case. Let's actually erase the image now because we don't need it anymore. So these are transformations. And how about for a general formula for our triple integral? So I need to show you the transformation factor as well. Your transformation factor here is just what you turn dv into. So for polar coordinates again, your transformation factor, dA is equal to r dr d theta. Your transformation factor is just the r here, the r value. So for dv, it's actually rho squared sine of phi. D rho d phi and d theta. Now again, I will actually teach this later. It's actually what we call a it would be on your unit on Jacobians, but for now just memorize that because that is a later topic in calculus 3. So remember this is your transformation factor. It is what you multiply your function with, and you're going to have your triple integral with your function now transformed using rho, phi, and theta in your function, multiplied by dv. And remember what dv is equal to? dv is equal to rho squared sine of phi dp d phi d theta. And again, the order in which you integrate does not matter. And you're going to have some bounds, I don't know, a, b, it's probably like some of it's called alpha or beta or something. I don't know. The rest I'll just call it c, d, e, f. Now just a quick end to the video. Whatever radius you have will, if you want to find the hypervolume integrated over some volume using a triple integral, whatever radius you have, it will just be from 0 to your radius of your sphere. Your phi value will be from 0 to pi because that is the maximum phi value that you could have to encompass an entire sphere when you're integrating. And your theta value is from 0 to 2 pi. So if you have any questions, put it down in the comment section.